We've talked about regular binary search trees, which have an average case time complexity of big O of log n, but they have a worst case time complexity of big O of n. Further, when we figured out that they have an average case time complexity of big O of log n, we had to make some somewhat unrealistic assumptions. To mitigate this, we introduced the randomized search tree, which is an extension of the binary search tree, but which makes the assumptions a little bit more reasonable. So it also has an average case time complexity of big O of log n for find operations, but it doesn't have to make as unrealistic of assumptions. However, the worst case time complexity is still big O of n. So the question is, can we somehow come up with another extension of a binary search tree, but that has a guarantee of big O of log n time complexity in the worst case? So we'll talk about AVL trees, which are one other extension of binary search trees that do indeed achieve big O of log n worst case time complexity for find, insert, and remove. Before we talk about AVL trees, we first have to introduce this concept of balance factor. So in a tree, the balance factor, or I guess in a binary tree, the balance factor of some node is the height of the right subtree of that node minus the height of the left subtree of that node. So an AVL tree is a binary search tree, so it is a binary search tree. All AVL trees are binary search trees, but it's a binary search tree in which every node has a balance factor of either -1, 0, or 1. So either the balance factor is 0 or it's off by 1. Nothing more significant than that. So here I have two examples of binary search trees. Let's first draw out the balance factors of each node in each tree, and then we can talk about AVL tree properties. So in this tree, I'm going to start at the leaves and go up. So we know that leaves by definition have a balance factor of 0 because their left height and the right height are both 0. There's no edges on either side. So I'm just going to label the balance factors of the leaves real quickly, which are super easy. So now let's go up. So this node has a height of 0 on the left, and it has a height of 1 on the right. So its balance factor is 1 minus 0, which is 1. This node has a height of 0 on its right and a height of 1 on its left. Therefore, its balance factor is 0 minus 1, which is -1. This node has a height of 1 on its right side and a height of 1, 2 on its left side. So its balance factor is 1 minus 2, which is -1. This node has a right height of 1, 2, a left height of 1. So its balance factor is 2 minus 1, which is 1. And now the root has a right height of 1, 2, 3. Remember, height is the longest distance to a leaf. On its right side, E has 1, 2, 3 edges to a leaf as its longest distance to a leaf. So 1, 2, 3, right height is 3. On its left, its height is 1, 2, 3. Therefore, its balance factor is 3 minus 3, which is 0. So in this tree, every single node has a balance factor of either 0, 1, or -1, which means this is indeed an AVL tree. It's a binary search tree in which every node has a balance factor of 0, 1, or -1. Let's look at this tree. So first, again, I'm going to fill in the balance factors of the leaves because those are easy. They're just 0. It's 0 minus 0. So I'm just going to fill in all the leaves because that's easy. Okay, now the internal nodes. So this node has a right height of 1, a left height of 1. So its balance factor is 1 minus 1, which is 0. This node has a right height of 1, a right height of 0, a left height of 1. So its balance factor is 0 minus 1, which is -1. This node has a right height of 1, 2, a left height of 1. So its balance factor is 2 minus 1, which is 1. This node has a right height of 2, and a left height of 0. So its balance factor is 2 minus 0, which is 2. This node has a right height of 1, 2, 3, a left height of 1, 2, 3. Therefore, its balance factor is 3 minus 3, which is 0. So even though this tree looks pretty balanced, and it's a binary search tree, we have a balance factor that is exceeding what we're allowed. We're only allowed -1, 0, or 1, but this tree has a balance factor of 2 in one of the nodes. Even though it's only one node that has this messed up balance factor, still we have a node that has an invalid balance factor. Therefore, this is not an AVL tree. So this one was an AVL tree. This one is not an AVL tree.